Welcome to this session. I am Bernard Keller from the City University of Paris. First, a technical announcement. This will be a pre-recorded talk and there will be no time for live questions at the end, but you can ask your questions in the Discord channel number 4 for algebraic and complex geometry. And now it's my pleasure to introduce Olivier Wittenberg from the CNRS at Université Sorbonne Paris Nord, who will speak on some aspects of rational points and rational curves.
Okay, so this lecture will be centered around two theorems that I'm going to present to you in two very different contexts. Let me start by stating them. So the first one is in number theory, Theorem A, which was obtained jointly with Jonathan Harpas from Paris. The date is 2020, publication date. It's about the inverse Galois problem, or a refinement of it. So let K be a number field, let G be a finite nilpotent group, and fix finitely many places V1, Vn, places of K, that do not divide the order of G. Then the theorem has two statements. The first is there exists a Galois extension, a field capital K, with Galois group G. So this part is not new. It had already been proved by Shafarevich, who more generally proved it for solvable groups. You can always find Galois extensions of a given number field with Galois group, your given solvable group. What is new is the second part, which says that the completions of this extension capital K over small k above the fixed places V1 to Vn can be prescribed freely. So freely among what? Well, one necessary condition is that when you complete, you obtain a Galois extension whose Galois group is a subgroup of G, and that's the only necessary condition. That's what the theorem says. So it can be prescribed freely among Galois extensions of the completions KV1, KVN, whose Galois groups are subgroups of G. Okay, so that's the statement. So again, the point is the second part. In other words, you can solve the inverse Galois problem over a number field K with local conditions at any finite set of places, with arbitrary local conditions at any finite set of places that do not divide the order of G. So this is what's new, and the point is that this was not accessible with Shafarevich's methods. Now, the second theorem that I want to present is a theorem in algebraic geometry, more precisely in real algebraic geometry, Theorem B, which was obtained jointly with Olivier Benoit from Paris too. Date year of publication 2021. So here, let X be a smooth, proper algebraic variety of the reals. And let me assume that it's birationally equivalent either to a homogeneous space of a linear group. Here I mean a connected linear group over R, of course, or let's say to a smooth cubic surface, hypersurface, smooth cubic hypersurface of dimension at least 2. So defined by one equation of degree 3 in a projective space. Okay, so these are the varieties that we're considering. And what we're doing is we're looking at loops, continuous loops, in the real locus, so in the space of continuous loops. So what is this? It's a continuous map from the circle to the real locus of R. So in the space of continuous loops, we can find, we can approximate, the statement is we can approximate any continuous loop by a rational algebraic one. So the rational algebraic loops are dense. So let me come back to this in a minute. Are dense with respect to the compact open topology. So here, what does this mean? So S1, the circle, is also the real locus of the projective line. So what do I mean? Whoops, sorry. What do I mean by a rational algebraic loop? I mean a loop, a continuous loop, which comes from a morphism of algebraic varieties. Coming from a morphism from the projective line over the reals to X. So this is morphism of algebraic varieties. On the real points, it gives you a continuous loop, and loops obtained in this way are the rational algebraic ones. So that's the statement. So just to make a picture, you can imagine, for example, that X is a cubic surface with two connected components of the real locus. In this case, you will get a sphere and a real projective plane. And what the theorem tells you is that if you draw a continuous loop in either of the components, say here, you can find in any Euclidean neighborhood of this loop, so very close to it, you can find another loop which happens to be algebraic, and more than that, it's a rational algebraic curve. Okay, so either here or in the other component, anywhere you like. So this type of approximation result is well known to hold if you're looking at loops inside affine space. This is the Stone-Weierstrass theorem. But the point is that we're going beyond such things. In fact, it's the first example of a variety which satisfies this approximation condition and which is not rational over the reals. And the theorem goes much further than that, since X here need not even be geometrically rational. Okay, so that's the two statements I wanted to show you. And what connects these two statements together is that their proofs, as you will clearly see, both go through the study of rational points of so-called rationally connected varieties over non-closed fields. And what is more, the two proofs in fact follow the same general strategy, which might look a bit surprising, but that's how it is. And so there's an interesting pattern that emerges from these proofs, and which allows one to dream that maybe some analogous theory might exist over other fields of interest. So I hope to get to this point at the end of the talk, but for now let me start by describing this common general strategy, first in the case of Theorem A, the theorem in number theory. So on Theorem A, so we have this, sorry, the statement is here. We have this number field and this group G. We're trying to construct extensions of K with group G. So the first step is to embed G into SLN of K. You fix some embedding, embedding of G in SLN of K for some n. And this you can always do. You can always make the symmetric group act by permuting the basis, the canonical basis. So for n large enough, this works. And then we view G as a group of, as a, say, a subgroup scheme, closed finite subgroup scheme of SLN viewed as an algebraic group over K now. I still write it SLN. And we consider the quotient of SLN by the right action of G by multiplication. Okay, so let me give a name to this map. It's pi. It's étale because G acts freely. And so that's what one calls the G torsor. It's a torsor under G, which means that G acts simply transitively on the geometric fibers. More than that, it's what one calls a versal G torsor, which means that not only is it a G torsor, but any G torsor over the spec of any field extension of K comes, it can be realized as a fiber of this pi over some point of SLN mod G. So looking at the fibers gives you all G torsors over all field extensions of K. So now, thanks to this versality property, we can reformulate the problem. So the goal now is to find a rational point of this quotient. Let me give it a name V. Find x in V of K. That is, so this will give us a torsor under G. And we want it to be close enough to given local points XVI in VKVI for I equals 1 to n, and such that the fiber of pi at x is irreducible as a scheme. So why is this exactly what we want to do? Well, if the fiber is irreducible, then it's going to be spec of some field. And now if you have a field extension of small k, which at the same time is a G torsor, then it has to be a Galois extension with group G, because G acts simply transitively on this geometric fiber. So such an X here will give us a Galois extension as in part 1 of the theorem. But in addition, so part 2 gives us, so we've prescribed the completions, so that means we have some G torsors over KV1, KVN, and by the versality property, these will correspond to KVI points of the base. So that's what we have, and if X is close enough to the XVIs, then by Krasnow's lemma, the field extension we construct here will have the specified completions. So the point here is we've reformulated now the question into a problem of finding appropriate rational points on a certain algebraic variety. So this is a in general difficult problem. It's in some cases it can be done. So Hilbert tells us by Hilbert's reducibility theorem, yes, you can do this if V is rational over K. But unfortunately, V is not even geometrically rational in general, so this doesn't work. So then what do we do? Well, in general, when you study rational points over number fields, you know that the geometry of the variety is going to influence very much the behavior of rational points, but even the conjectural picture is far from complete in general. However, here we are looking at a variety with a very special geometry. It's a unirational variety here. And for unirational varieties, we do have a satisfactory conjecture concerning the rational points. And I'm going to recall this now. But first, let me mention that it would be even better if we could construct not just rational points on V, but even rational curves. Because then, by constructing rational curves, we would be solving the regular inverse Galois problem over K, which is constructing covers of P1 with Galois group G and which are geometrically reducible. But unfortunately, for rational curves even on unirational varieties, we don't even have a conjecture that would predict the existence of sufficiently nice rational curves. So we have to be happy with rational points. So the conjecture is the following. Conjecture 1, so due to Couliot-Hélène, it's not just about unirational varieties, but even rationally connected varieties. So let me recall this. X will be a smooth, rationally connected variety over our number field K. So rationally connected means it's a purely geometric notion. It means that for any algebraically closed field extension, you can connect any two general points over this algebraically closed extension by a rational curve. So any two general K prime points can be connected by a rational curve defined over K prime. So this is a purely geometric notion. And for example, so unirational varieties or geometrically unirational varieties are rationally connected because you can use the lines on a projective space to connect two general points. So under this assumption, there's a very precise conjecture about rational points. The conjecture says that if you look at the set of rational points, you can embed it diagonally into the product over all places, place of K, of the local points, and it tells us exactly what the closure of x of k should be in this topological space. And this closure should exactly be the Brouwer-Manin set. So this is the set of collection of local points that are orthogonal to the unramified Brouwer group of X. So let me not go into the details of the definition of this. I will just say that this was defined by Manin in 1970, actually in his ICM talk. So this is something that uses the Brouwer group of schemes defined by Grothendieck and class field theory, both local and global. Essentially, it tells you that those collections of local points that can be approximated by a rational point are those that satisfy a certain reciprocity, global reciprocity condition given by every class in the Brouwer group of a smooth projective model of X. So let me not discuss the details of this. Sorry, the statement is this is dense. Conjecture is this is dense. But I would like to point out that if this conjecture is true, then you get many things. First, you get a concrete criterion to decide the existence of a rational point on X. In fact, the right-hand side is often rather easy to calculate in some sense. And more than that, if a rational point exists, it tells you that rational points are Zariski dense. There are many of them. And even more than that you can find them in any Hilbert subset of X. So that's exactly in this situation here, you can find many rational points such that the fiber is irreducible. It's a consequence of such a statement. So in particular, the conjecture would imply the inverse Galois problem for all finite groups. So it's completely out of reach. But still, it can be shown to hold in some cases. So some methods have been developed to attack this conjecture. And among them, I would like to list two methods. So there's the descent method. So this goes back to descent à la Fermat, developed by Mordell, Castles, and so on. But in its present form, it's like this. So you fix a torsor, y to x. So you're interested in x. Y to x is an L torsor, where L is some linear algebraic group over K. And now if you have a cohomology class, sigma in H1 KL, you can twist your torsor by this class or by the cocycle underlying this class, and you get a twist, y sigma to x. Now the hope of the descent method is this. If all of the twists satisfy conjecture 1, then so does x. Okay, so it tells you that to prove conjecture 1, you can reduce yourself to the twists of any given torsor under a linear algebraic group. So that's the hope. It's not a theorem, it's a hope. Well, it's a conjecture, if you like. In many cases, this has been proved, but it's not known in general. But still, it's a tool that's useful in many situations. The second tool that's been developed for this conjecture is the fibration method. So now we suppose that X has the structure of a fibration over an I-space. So let's say X to Y, say dominant with rationally connected generic fiber. So X and Y are themselves rationally connected. And the hope now is if Y, the base, and the fibers, let's say the smooth fibers, above rational points of Y satisfy conjecture 1, then so does X. So again, the hope is to reduce conjecture 1 for X to conjecture 1 for some possibly simpler varieties, the base of our fibration and the fibers. And again, this is not known in general, but many cases are known, so that it's been used really as a systematic tool. So now that I've said everything about conjecture 1, I can tell you what the proof of theorem A really is. Well, in fact, one proves theorem A prime, which is homogeneous spaces of SLN with finite supersolvable stabilizer satisfy conjecture 1. So supersolvable is something between nilpotent and solvable. Let me not enter into details here. And also I should mention that here the condition of supersolvability is not purely group theoretic. It takes into account the action of Galois on the stabilizer. It's an outer action. Okay, but anyway, this is the statement, and in particular you can apply it to SNN mod G. This is an example of a homogeneous space. Of course, here the point is all homogeneous spaces are not of this form. In particular, they don't all have rational points. And even then, we need to know theorem A prime in this generality for the proof to go through. So let me not explain the proof. I will just say that it results from a combination of the descent method and the fibration method applied to the variety V based on a geometric dévissage. So I will just draw a diagram to show you the geometry. So here we have V, and it turns out that one can construct a torsor under a torus, an algebraic torus T, W, which then has a map to a quasi-trivial torus, that is a torus of the form Veil restriction of scalars of GM from some étale algebra, such that the fibers here, the fibers are homogeneous spaces of SLN with stabilizer a strict subgroup of G. So a smaller stabilizer, which is going to be a subgroup of G. And now we see what appears. It's a proof by induction. We're going to induct on the size of the stabilizer, and if we know the results in this generality for smaller stabilizers, then here we can hope to get conjecture 1 for W starting from conjecture 1 for the base, which is easy because the base is rational, and from conjecture 1 for the fibers, which is the induction hypothesis, by applying the fibration method. And then here we will apply the descent method to go back from W and its twists to V. So that's the general strategy. Of course, there's lots going on here that I'm not explaining, but that's the geometry underlying the proof. And of course, you have to prove that the fibration method and the descent method work in the cases where we need them here. But that's what we do. Let's now go back to Theorem B. So the statement is this one. We have this variety X, and we're trying to approximate continuous loops by rational curves. So this property is simply not good enough. First of all, it's not in any obvious way, at least, a birational invariant. To get a birational invariant, to be able to have compatibility with blow-ups, for example, we need to look at rational curves which not only approximate continuous loops, but which also pass through given points of these loops, or even points with tangent vectors and so on. So this is one thing. But another thing which is more serious is, suppose we're trying to exploit the structure of a fibration. Say X has a map to Y, and Y is a variety for which we already know the property, this approximation property, and the fibers as well. And say you try to approximate a continuous loop on X like this. So the ideal situation is when the image of this loop in Y is already a rational algebraic curve. So let's assume we're in this situation. Then what can we do? We're not going to squeeze the loop inside a fiber of this map. So knowledge of the property for the fibers of the map is not going to be enough to deduce it for X. However, one thing we can do is consider the fiber of this map not over a real point of Y, but over the generic point of this rational curve here. And this will definitely contain the whole situation. If the map here is 1-to-1, we will obtain, by restricting the map over the rational curve, we will obtain a family of real varieties over a curve with a continuous section. And this maybe we can approximate. So here, the whole point to get to perhaps the possibility of a fibration argument is that we need to work not with real varieties, but with families of real varieties over a curve. So this leads us to the main definition that underlies the proof of Theorem B, which is the definition of the tight approximation property. So this is a property for smooth varieties, not over the reals, but over the functional field of a real curve. So I will say that X satisfies tight approximation if whenever you have a proper regular model of X over B, say script X, so this is a proper map, script X is a smooth variety of the reals, and the generic fiber is birationally equivalent to capital X. So whenever you have such a thing, so let me draw a picture here. Okay, this is script X mapping to B, and so the generic fiber is birationally equivalent to X. So whenever you have this and a continuous section, let me call it S sub R, so from the real points of B to the real points of script X. Okay, and let's assume for the statement, it's not just continuous, but say a sinfinity section. Okay, so let me draw it here. We have a sinfinity section, and in addition, we're going to fix finitely many points of B, B1, Bn, in B of R, and an integer capital N. So the points are here, B1, Bn. So the property is that whenever you have fixed all of this data, there exists an algebraic section, so morphism from B to script X, such that on the real points, it's arbitrarily close to our given sinfinity sections. So S restricted to the real points is arbitrarily close to SR. And in addition, we want S to go through the same point as SR above B1, Bn. And not only this, but we want them to have the same Taylor series up to order capital N. So let me briefly write this as and they coincide, sorry, at the BI to order N, to order, yeah, at least N. So here, so we're fixing the points here and here also, and also the tangent vector, and so on up to order N. And so we're looking for an algebraic section which is very close in the compact open topology. So this is in the compact open topology as before. So very close in the Euclidean neighborhood here, and passing through the same point with the same Taylor series here. Okay, so that's what we consider. So the point of this property is that, first of all, it implies the property that we're interested in. You can apply this if it holds. Let's say you apply it to a constant variety, so X, a variety defined over the reals. You just extend the scalars to the function field of B, and take B equals P1. This will give you maps from P1 to your real variety. So this will give you rational curves on your variety. But the point is that it is flexible enough to allow for descent and fibration arguments, unlike the previous property that we were considering for real varieties. So here we're in a very analogous situation as in the case of Theorem A. We have conjecture, so conjecture 2 that we make with Olivier Benoit, that smooth rationally connected varieties satisfy so over the function field of a real curve, satisfy tight approximation always. And what we can prove is that the descent and the fibration method work in full generality in this context. So for conjecture 2, descent and fibration, the descent and fibration methods work in full. So by this I mean, if you go back here, so I wrote two hopes. So what I'm saying is if you replace conjecture 1 by conjecture 2, then these two statements are theorems. So this gives you a way to prove tight approximation for many varieties, starting from the case of Pn, which you have to prove separately. And it's in this way that Theorem B follows. So, okay, you have to apply, okay, Theorem B follows from this plus the case of projective space. And let me emphasize that it's really crucial here that we're looking at varieties defined over K and rational points of these varieties over K, and not just at real varieties, even though at the end we're interested in rational curves on real varieties. During the geometric dévissage that are underlying the proofs, we do consider non-constant varieties, even if we start from constant varieties. So for example, in the case of cubic surfaces, well, over the reals, take a cubic surface over the real, it's birationally equivalent to a conic bundle over P1. So you have a fibration structure, you have to prove the theorem for conics and for P1, and then you get it for cubic surfaces. And then if you get it for cubic hypersurfaces by fibering by hyperplanes. Okay, and so on. So this is the situation, and as I've explained, since the same strategy works here for these two theorems in two very different contexts, this leads one to wonder what happens over other fields. So let's say, for example, that we're interested in the regular inverse Galois problem over Q. And let me recall that it's completely open even when G is a nilpotent group. So in other words, we're looking at rational curves on SLN mod G over Q, where G is nilpotent. So rational curves over Q, that's the same as rational points over Q join T, as we've learned in the real situation. And a natural approach, if you want to understand rational points over Q join T on this space when G is nilpotent, is to try to imitate the proof of theorem A, but now not over Q, but over Q join T. The problem is we don't even have an analog of conjecture 1 for rational points over such fields. So we're not going to apply the geometric dévissage that I told you about and the descent and fibration method for a conjecture that we don't even have. So let's be less ambitious, and as a first step, let's replace Q by its completions. So first, over the reals, well, that's the story that I've already told you. We do have a good property here and a good framework, the tight approximation property for rational points over R join T. So then what happens over QP? So we're looking at rational curves over QP and at rational points over QP join T. So on this variety or any rationally connected variety. So, well, that's the what the strategies of the proofs I told you suggests. If there's a real story, maybe there's a p-adic analog. So that's the challenge. Well, there should be some p-adic version of the tight approximation property. So formulate a p-adic tight approximation property for the rational points of rationally connected varieties over this field, for rational points of rationally connected varieties over QP joint T. And this formulation should satisfy two things. First, it should be precise enough to yield concrete criteria for the existence of a rational point. As conjectures 1 and 2 do of a number fields and of a function fields of real curves. So over number fields, the criterion is the Ramanin set should be non-empty, and over function fields of real curves, the criterion is when you take a model, there should be some C-infinity section on the real locus, and that's it. This should be enough. And the second thing is that the formulation should be flexible enough that the descent and fibration methods can be applied. So here, one motivation behind the first thing I wrote here is the general question, is there an algorithm for deciding the existence of rational points on smooth rationally connected varieties over QP joint T? So this is, as far as I know, a very open question. If you remove the hypothesis that the variety be rationally connected, then the answer is known to be no. It's the negative answer to Hilbert's 10th problem over this field. But as far as we know, for rationally connected varieties, it could very well have a positive answer. In the same way, over R adjoint T, Hilbert's 10th problem has a negative answer, but if you restrict to rationally connected varieties, then conjecture 2 would imply a positive answer. And similarly over Q, conjecture 1 would imply a positive answer for rationally connected varieties, while for arbitrary varieties, the question is open, but presumably the answer is no. And for the second thing here, what I have in mind is if you can apply the descent and the fibration method, then hopefully you should be able to recover all known results about rational curves on rationally connected varieties over QP and on rational points of rationally connected varieties over QP adjoint T. And here I'm thinking, for example, of Harbeta's result from the 80s that the regular inverse Galois problem has a positive solution over QP. So this means one can construct appropriate rational curves on SLN mod G over QP for any group G. So this has been revisited and understood and extended many times since, but that's the result I have in mind. And so that's about rational curves over QP, and about rational points over QP joint T. Let me quote the result of Parimala and Suraj from 2010 for P different from 2. If P equals 2, this is due to Heath, Brown, and Leap. That the U invariant of QP joint T is equal to 8. So this means any smooth projective quadric of dimension at least 7 has a rational point. If you could do all of this, then this theorem would follow immediately, because you could fiber by hyperplane sections to get the dimension of the quadric down to 1, and rational points of conics over QP joint T are very well understood thanks to the work of Tate and Lichtenbaum. Okay, so that's it. Thanks very much for your attention.